Hi guys. Yesterday we started working on simplifying radical expressions. We learned that there are two main methods for doing this. You can make a factor tree, and then for every pair of factors take out one. But really what you're doing when you do that is you're actually taking out perfect squares. You're not taking them out, you're doing the verb, you're actually square rooting those parts. So let's get into more of that. Everybody get out page 9 in your math binder. Make sure you have page 9 ready, some pens, some pencils, whatever you need to take your notes. And let's learn more about simplifying radicals. Okay, check this out. The very first thing I did on the top of page 9, and I would love for you to do the same, is I made myself a list of the first 12 perfect squares. These are the first 12 because they come from squaring the first 12 whole numbers. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. They keep going. Okay, if you keep squaring things, you keep getting perfect squares. But this is a good list to have handy and have those in your brain. If you don't memorize them, that's okay, but you should be able to recognize them. So anytime you need to make a list of perfect squares, or if you just make it on the top of this page 9, then you can use this page throughout all of your practice. There's another list I'm going to share with you that I actually find even more helpful as I'm trying to do that, trying to do this, as in simplifying, but I'll get to that in just a second. So let's actually, in these boxes, in boxes 1 and 2 right here, I'm actually going to draw a line here down the middle because I'm going to show you, for the first few of these, I'm going to show you both methods that we learned yesterday. The factor tree, factoring all the way down to the prime factorization, and then for every pair taking out one. And I'm also going to show you the largest perfect square factor. And then you can decide as we work on these. You're not going to have to do both ways on everything. You can decide which way makes more sense to you, which way works better for you, and then continue using that way. And you can switch back and forth. If you have one that you're like, hey, this method isn't working for me, you can try the other one. So let's come to a factor tree first. All right, so you practiced some of this prime factorization on your practice yesterday. The nice thing about this method is it does not matter what factors you start with. So for 28, I'm going to go, the first thing I think of is 4 and 7. You could do 2 and 14, but we're not all the way done. As soon as you reach the ends of all of your branches and get prime numbers there, then you're done. Yes, absolutely, you could go 2 and 1, but then your factor tree would go on forever. So the thing I want you to remember as we work through this process is that square root of 28, I haven't actually done the square root. I haven't done that action yet. All I've done, the only action I've done is factor. So I need all of this under the radical still. Okay, so when I say all of this, I mean the end of every little branch here. So I'm going to circle just the ends. Okay, so I have 2 times 2 times 7. And remember, with this process, you have to have a pair in order to take out 1. Because really what's happening is this is actually 2 squared, and then the squared and the square root cancel each other. Okay, so for every pair here, we can write it this way. Watch what this means. This means that we've got 2 squared times 7. Okay. And you can actually break it up, and you'll see as we do this a little further, but you actually are square rooting each of these separately, but you're only going to cancel the one that actually has its full inverse. So anytime you end up with a squared, because you have 2 factors there, the squared and the square root will cancel, and you get 2 square root of 7. Now if you're like, wait, how could that, they look so different. Remember, a way that you can verify this is if you type in square root of 28, you can see the decimal approximation. It's about 5.2915. And keep that in mind, if I do 2 square root of 7, the exact same decimal. So you can always verify if you did this correctly. Type in the original, type in the new one, see if they get the same decimal approximation. Okay, now the other method, so this is the factor tree method. The other method is largest perfect square factor. Okay, so I'm going to come over here and I'm going to write that square root of 28, and I'm going to go right to these factors I used right here. Square root of 28 is square root of 4 times 7. Notice the radical symbol is still there because I haven't done that verb yet. I haven't square rooted anything. All I did was factor. The only thing I've done so far is factor. Now I'm going to separate this out again. I'm going to go, okay, this is square root of 4 times square root of 7. I'm only going to actually do the square rooting part whenever there's a perfect square. So you can see you don't actually have to factor it all the way down if you have these numbers in mind. Instead of going all the way down to the prime factorization, instead of doing that, you can just look for these values. Look for numbers that are on this list. And if you get a number on that list, you can just square root it. Now we're actually doing the square root verb. Square root of 4 is 2. Square root of 7. 7 is not on this list. So square root of 7 is going to be a long, non-terminating, non-repeating, irrational number. So guess what? It stays inside the radical. Same exact result. You decide which way makes more sense to you and use that way. Okay, let's try this again. Number 2. Again, I'm going to start with a factor tree. Okay, anytime I see 100 or 300, 400, 500, I think of those factors first. So I'm going to say, okay, this is 3 times 100. Now that branch is done. 3 is a prime number. This is 10 times 10. This is 2 and 5 and 2 and 5. Okay, lots of factors here, so watch this. This is the end of my branches. I find it really helpful when I come back and put them in the radical. I find it helpful to put them back in order. So the factors that I have here, I'm gonna write it like this. I have 2 times 2, and I have a 3, don't forget the 3, and I have a 5 and a 5. Remember, for every 2, I get to take out 1, okay? Not for every 2, but for every pair, okay? Not the number 2, but a pair of factors. So these 2, I get to take out 1. These 2, what do I do with them if I take them out? Well, they are factors, so this is all still multiplication. So if you take out more than one value, you're going to times it. So I get to take out a 2, I get to take out a 5. The 3 is not a pair of factors, it's just by itself. So the 3 will have to stay inside. And your last step is clean this stuff up. These values up front, here is a word that you may not have heard since 7th grade. This value up front is called a coefficient. Coefficient. I'm going to write that word on the side here so you guys can see it as you hear it. Coefficient. This is a number. A coefficient in math is a number being multiplied on something. So like when we said 5x last year, the 5 was the coefficient. It's a coefficient on x. Radicals often end up with coefficients. These pieces that get to actually come out of this through a square root, the pieces that we actually take the square root of, become coefficients on the front. So this 10 is the coefficient, and the 3 is the number left inside. That does, in fact, have a fancy name as well. And I'm going to share it with you in a minute, just for the fun, because it's a fun word to say. Let's first look at the other process here. Okay, so instead of breaking it all the way down to all of these factors, what if instead we just find the largest perfect square? Okay, I'm going to tell you right now, this is where students often make a very common mistake. Students will often find in this method, the nice thing about this method is you can't really make this mistake. This method I think is faster, but we're more prone to mistakes in it. The number one mistake students make, are you listening? The number one mistake they make is that they find a perfect square, but it's not the largest one. So I'm going to share with you, for example, 25 goes into 300, but it's not the biggest one on this list. 100 also goes in. So sometimes we start dividing by perfect squares and we get a little lost or forget to keep checking. So before we go to that, I want to share with you a couple things over here, okay? First of all, some vocab. I am going to write this. X square root of, I'm going to use one more color here on the blue. And I just want to make sure you guys know, I wrote it over there and I'm going to write it again right here. This part is called a coefficient. Coefficient, there's another I in there. And this part, you ready for this? This is some fun language that you'll see on your Canvas quiz practice. So I want to make sure you know what I'm talking about. The part that stays inside the radical, it actually has a noun name as well. It's called the radicand. Isn't that fun? The radicand. So a lot of these, when you simplify them, you end up with a coefficient, a value being multiplied on the front, and a radicand, a value that's left inside the radical. So for example here, 10 is the coefficient, 3 is the radicand. Here, 2 is the coefficient, 7 is the radicand. Okay, so that's the first important thing I need you to know. Next important thing I need you to know is this, all right? If you have fully simplified a radical, I'm going to tell you right now some numbers that are allowed to stay inside, numbers that are allowed to be radicands. So we're going to say this, allowed to be a radicand. Not everything can be a radicand. I mean, it can be, but not if you've simplified it. For example, here, 28 is not allowed to be a radicand and call this simplified. Why? Because it has a perfect square in it. There's still a perfect square factor in it. There's a 4 in there. 300 is not allowed to be a radicand because there's a perfect square in it, okay? So what numbers are allowed to be left inside? What numbers are allowed to be a radicand? Very important list here, and I actually find this to be most helpful in this process. The smallest number that can be a radicand, 1 can be inside, but guess what the square root of 1 is? It's just 1, so you wouldn't, that would be super redundant. You wouldn't write that. 2 is often a radicand because 2 has no perfect square factors. 3 is often a radicand. Can 4 be a radicand? Not if you're simplifying it because 4 is a perfect square. 5 can be a radicand. 6 can be a radicand. And some students stop me there and go, wait, Ms. McGowan, 6 isn't a prime number. It does not have to be a prime number. In order to be a radicand, they just can't have any perfect square factors. So think of the factors of 6, 2, and 3. Neither of those are perfect squares. So 6 is very often a radicand. 6 will very regularly be left inside the radical. 6 can stay inside. 7, 8, oh no, not 8, do not write 8. Guess what is a factor of 8? 4. And guess where 4 is on this list? Any number that has a perfect square factor should never be left inside the radical, okay? So not 8, not 9, 10 is often left inside the radical. 10 can be a radicand because its only factors are 2 and 5. 11, what about 12? No, 12 has a 4 in it. Never leave a 12 inside of the radical. Never leave a 12 in there. If you have a 12 in there, you didn't finish simplifying it. 13, 14, 15, there's more, but that's usually the biggest you need. It's usually one of these first few, 2, 3, 5, 6, 7, or 10. Those are the most common. So do you know what helps me? Actually, I need a combination of these lists. I need to keep these both in my mind. But what helps me when I'm trying to find the largest perfect square is I actually start, if I look at this number that's the radicand right now, and I say 300, I actually start by dividing by these until I find one of these, okay? So, for example, and I just start with 2. I just always start with 2, unless it's not even. 300 divided by 2 is 150. Is 150 a perfect square? No, it's not. So that's not the right factor. 300, let's go to the next one. 300 divided by 3. Is that a perfect square? It sure is. If you start dividing by these numbers that are allowed to stay inside the radical, you will find your factors more quickly. We'll keep practicing that as we move forward. But that means I am actually now, for this other method, I know right away that I can go square root of 300 is equal to the square root of 100 times 3. I like to lead with the perfect square because then when I go like this, square root of 100 times square root of 3, now I can see, oh, here's the perfect square, and this is why I found it. I want to separate it out so that I only actually do the square root action on the perfect square parts because I don't want a big long decimal right now. I want to keep it in exact form. So this is 10 square root of 3. We already knew that, just a different method. Now, I'm going to tell you for 256, I'm going to show you, and I'm going to show you why I personally usually prefer trying to find the largest perfect square factor if I can. But 256, if I don't know factors of that, I'm just going to immediately cut it in half. Then I'm going to go, oh, I can cut this in half again. 2 and 64. I can go, okay, this is 8 and 8, and this is 4 and 2, and this is 4 and 2, and this is 2 and 2 and 2. Okay, this is a big tree. Sometimes you get these big numbers, and this is why factor trees can be a little tedious. And then sometimes even if you go through the whole thing, sometimes you miss a factor, so be careful of that. But what this means is square root of 256 is square root of 1, 2, 3, 4, 5, 6, 7, 8 of them. 2, 3, 4, 5, 6, 7. Oh no. I'm going to put one in the front because I don't want it to go over to the other question. And look at this. For every pair, I'm taking out a factor. Everything came out of the radical. There is no more radicand. Guess what that means about this original number? It was a perfect square. Watch. Square root of 256. It was a perfect square all along. So this answer is just 16. If you're given, if this entire radicand is a perfect square, you should have nothing left inside the radical. Okay? All right, on number 4, I'm gonna take you guys through, let's cut it in half this way. And then as we jump to the next couple of examples, we'll start to look at really which methods are more efficient, okay? So 98, I don't know factors of 98, but it's even, so 2 times 49. Do you recognize that number 49? That's gonna help us with the other method. But right now, let's keep going with this. And this tells me, here's what you have to be careful of on this one. This already has a coefficient. You notice that? We can't disregard that. We can't forget about that. That's really important. But it's outside of the radical. So it has nothing to do with square rooting stuff. So right now, I'm just going to leave it as a coefficient. It's already outside, so don't worry about it yet. Let's worry about what's inside. Here I go as my factors here. I have 2 and 7 and 7. Okay, I'm going to write that right here. 2 and 7 and 7. And for every pair of factors, I'm going to take out 1. Here's the deal though. If I already have a coefficient, I need it there. Don't forget about it. But now I'm also going to bring out another part of that coefficient. And the 2 stays inside. Clean this up. Multiply those coefficients. And there you go. Or you can, of course, jump right here to this. You can say, okay, here was my original. If you go with this process over here and you say, okay, I'm looking at the number 98. I'm not concerned about that coefficient at all. I'm concerned about the radicand. I'm going to start dividing by numbers that I know are allowed to stay inside. Divide by 2. Hey, look at that. Perfect square right away. That tells me I leave my coefficient and I can go straight to 49 times 2. This is a perfect square. Takes me right back to the same place. two methods: factor tree or largest perfect square. Okay, and when you're done with this, you're going to tell me for your submission today which way you like better and why. But let me take you through a few more examples first before you decide. Because there's one more thing that comes up here besides just regular simplifying. This is what you're going to practice on your Canvas quiz. This down here is going to help lead us into and help us get ready for tomorrow. Okay, one thing you need to understand and know about radicals, about everything in mathematics, is if you try to add or subtract things, you have to have them the same size. What do I mean by that? Well, like if you're adding fourths and halves, you can't add them until you get everything into fourths. You're getting things the same size. If you're trying to add inches to centimeters, you can't until you convert it all to centimeters. You have to get things the same size. That's true here for radicals as well. This means I can only combine square roots of 5. That's a size now, like fourths or centimeters. I can only combine square roots of 5 with other square roots of 5. So let's take a look at the coefficients here. This, if there's nothing there, there is of course always something there. That has a coefficient of 1, and the radicands are the same. So let's make a note here on the side to add radicands must be the same. Remember, radicand means the number inside the radical. Hey, look, they are the same. So I can combine them. And when I do that, they're going to stay the same. Just like fourths plus fourths is still fourths. Centimeters plus centimeters is still centimeters. Square roots of 5 plus square roots of 5 is still square roots of 5. So all we have to do is combine the coefficients. So 1 minus 3 is -2, and you leave the radicand. It's like combining like terms. 1x plus 5x is 6x. Okay, now what do I do? Here's one more right here. Can I combine those? I sure can. And then you know what I'm going to do? Here's a coefficient of 1. The radicands are the same. 1 plus 2 is 3. But you know what? I'm not actually done with that because that radicand is not simplified. Let's practice our largest perfect square. Okay, here's my list of stuff that's allowed to stay inside. I'm going to start dividing this radicand by those things. Here I go, 150 divided by 2 is 75. Look at the top of your paper. Is 75 a perfect square? No, it's not. Okay, let's try 150 divided by 3. Is 50 a perfect square? No, it's not. Let's try, I'm going through this list right here, dividing by 2, 3, 5, 6. Go from there. So I'm going to skip 4 because that's not, I'm going to do 150. I did 2 and 3. Now I'm going to divide by 5. Is 30 a perfect square? No, it's not. Go to the next one. 150 divided by 6. Is 25 a perfect square? Yes, it is. What did I do? I did 6. So here's my factors right here, 25 and 6. If you go with this list of things that are allowed to stay inside, you will find your perfect square factors more quickly. So here's what this turns into. 3 is already a coefficient. You need it there, leave it there. I'm going to factor now. This is 25 times 6. I'm going to square root now, but only the perfect square part. 3 times 5, square root of 6. Notice the 5 is now outside. I square rooted it, it gets to come out, and it's a 5 now. The 6 stays inside. This one gets to be square rooted, this one doesn't. Now I just get to clean things up. 3 times 5 is 15, square root of 6. Okay, I'm going to take you through just a quick think aloud, and I'm going to just share out loud my thought process. These last couple problems are kind of big. When you're finished with them, just take a little breath and know Mrs. McGowan is going to help me practice these more before I'm expected to do these on a quiz or anything. So don't panic about that. I'm trying to get this stuff up. Okay, so follow with me, write things down. If you don't fully understand these last two, don't panic. It's okay. You're going to get more practice on it. But let's give this a try. So here we go. I am going to start by figuring out the largest perfect square factor of these. And I'm going to do that by dividing by things that I know are allowed to stay inside. I always start with 2. And guess what? 72 divided by 2 is 36. Look at the top of your paper. Is 36 a perfect square? Yes, it is. 36 times 2. I'm going to rewrite that right now. Minus the 4 stays there. Keep writing, keep listening. 98 divided by 2, we actually did that one earlier. Gives me a perfect square. 45 is 9 times 5. I know that works because 5 is on my list of things that's allowed to stay inside. Okay? All I've done so far is factor. What's all I've done so far? Factor. Now I'm going to actually square root. That's the verb, that's the action I'm taking now. But I'm only going to square root the parts that come out nicely. Okay? Square root of 36 is 6. Because I could square root it, it's out of the radical now. It's a coefficient now. The 2 must stay inside because I didn't actually square root it because I don't want that big decimal. The 4 was already outside. I'm going to bring a 7 out with it. Why a 7? Because the square root of 49 is 7. Do I get to square root the 2? No, I don't. Stays inside. Square root of 9 is 3. I actually got to square root it. It comes out of the radical. 5 has to stay inside. Okay, let's do a little cleanup right here. Didn't do anything with that. Let's multiply these coefficients. I can only combine anything that has the same radicand. That means I can put these 2 terms together. This guy won't be able to. 6 minus 28 is negative 22 square root of 2. And I just tack that guy on. And the only other thing I could do at this point is give a decimal approximation, and I don't want that, so I stop right there. One more. I'm not even going to say anything. I'm just going to do, and you watch. Again, if you don't fully grasp this one, it's okay. We'll get more practice. $250. I immediately think 25 times 10. Is 10 allowed to stay in the radical? Yes, it is. No, I'm out of room. Hate when that happens. There's a +7 right there. I should have squished it more. Okay. Here I go. Those are the only things I can square root. I'm going to clean that up. Here's what I can put together. See that, that. All of those have the same radicand. So here I go. 2 minus 5 is -3. -3 plus 10 is 7. And those are just regular old numbers. Combine them. Do not put those together because that has a square root of 10 and that doesn't. Now, if those last 2 examples you're like, whoa, it's okay. Take a step back. See how you feel about these up here. These 4 up here are what you're practicing on your Canvas quiz today. Tomorrow, we're not learning anything new. We're just practicing more of this and trying to put it together with adding and subtracting. So now you just get a lot of practice on this. Email me if you have any questions. Email Ms. Johnson. Ask your math teacher for help. And good luck.